Welcome to this tutorial on simulated NMR spectrum using JMOL. In this tutorial, we will learn to predict the proton and carbon-13 NMR spectra for organic molecules using JSpecView. Change the display parameters of the plot. Integrate the peaks in the proton NMR spectrum. Stack two or more spectra. Combine two spectra. Save the spectrum in JDX format. Export the spectrum in various image file formats. Here I am using Ubuntu Linux OS version 20.04, JMOL version 14.32.80, Java version 11.0.16 and working internet connection. To follow this tutorial, learners should be familiar with nuclear magnetic resonance spectroscopy analysis for organic molecules and basics of JMOL interface. For the prerequisite JMOL tutorials, please visit this website. The input files required for this tutorial are available in the code files link. Please download and extract the files. Make a copy of all the files and then use them for practicing. JSpecView is a graphical viewer for spectral data in the JCAMP-DX format. Here is the link for more information on JSpecView. JSpecView has been integrated into the JMOL distribution. The simulated proton and carbon-13 NMR tools have been added in JMOL in the Tools menu. Here I have opened the JMOL interface. I will begin the demonstration with a simple aromatic amine aniline. Open the File menu and click on Get Mol option. A dialog box opens. Type aniline in the text field. Click on the OK button. A model of aniline loads in the panel. Let us get the simulated proton and carbon-13 NMR for this molecule. Open the Tools menu in the main menu bar. Scroll down and select Spectra. From the submenu, select Simulated 1H Spectrum option. Wait for a few seconds. The simulated proton NMR for aniline molecule opens in a JSpecView window. You will see the 3D model of the molecule in the left panel. The simulated spectrum is seen on the right panel. In the simulated spectrum, the x-axis is the energy axis. The energy axis is called delta axis. The units are given in parts per million. Most often, the signal area for organic compounds ranges from 0 to 12 ppm. The y-axis shows the intensity of the signal. The spectrum for aniline shows 3 sets of signals. These correspond to the 3 sets of protons on the molecule. Hover the mouse over the peaks. The value of the chemical shift is displayed on the spectrum. Click on any signal on the spectrum. The corresponding protons are highlighted on the 3D model in the left panel. Click on any hydrogen atom in the model. The corresponding peak is highlighted in the spectrum. This feature allows us to analyze the spectrum easily and assign the peaks. Left-click and drag the mouse on the peaks from left to right to expand the peaks. We can repeat this process a couple of times until we see the splitting clearly. Now we see the splitting of the peaks clearly. The center of the peak is indicated as a red tick mark on the top of the graph. Click on the red tick. The delta value of this peak is displayed. In this spectrum, we see a triplet around delta 7.24, a triplet around 7.03, a doublet at 6.77. Let us analyze the peaks. I will start from the left side of the spectrum and click on the peak at delta 7.24. The hydrogens on metacarbon are highlighted. This peak corresponds to hydrogens on metacarbon atoms. This hydrogen interacts with two neighboring hydrogens. Hence, this peak is a triplet. Now click on the next set of signals at delta 7.03. The hydrogen on the para carbon is highlighted. This hydrogen interacts with two neighboring hydrogens. Hence, this peak is a triplet. Now click on the peak at 6.77. The hydrogens on the ortho carbons are highlighted. This hydrogen interacts with only one neighboring hydrogen. Hence, it is a doublet. The protons on metacarbon atoms appear downfield when compared to ortho and para carbons. The metaprotons are de-shielded. This is due to the resonance effect. The lone pair on the nitrogen is involved in the conjugation. The electron density is less at meta position and more at ortho and para positions. Please refer to the additional reading material for more information. Back to the JSPEC view window. The ortho and para hydrogen atoms are shielded when compared to meta. Hence, they appear upfilled. Right-click on the spectrum to open the context menu. Here we see several options. I will select Integration. A window Integration for 1H NMR simulated opens. Leave all the settings as such. Click on Apply. Notice that on the spectrum, the integration of the peaks is displayed. The ratio of intensity corresponds to 2:1:2. This corresponds to 2 metaprotons, 1 paraproton, and 2 orthoprotons. The table of values will also be displayed in the integration window. Close the integration window. At the far right end of the spectral window, you will see two black arrows, one upward and one downward. Click on these arrows to increase and decrease the peak heights. Click on the small circle between the two arrows. This will display the original spectrum. Let us again expand the peaks to show the splitting of the peaks clearly. We can change the display scheme of the spectrum according to our preference. Click on Options on the top menu. Here you will find checkboxes to hide or display toolbar, side panel, and status bar. I will leave them all checked. Select Preferences option. Preferences dialog box opens. Click on the Display Scheme tab. I will resize the Preferences window to see the options clearly. Various parameters can be changed for the elements listed here. As an example, I will change the color of the plot to pink. Under the Elements section, select Plot. Select pink from the color scheme. Click on OK at the bottom of the dialog box. Note the pink color peaks in the plot. We can add more spectra to the panel. We can compare the spectrum of aniline with the spectrum of any other compound. For example, I would like to compare it with the proton NMR spectrum of benzene. Click on the File menu. From the options, I will select Add H1 Simulation. Open URL dialog box opens. Type benzene in the search field. Click on the OK button. Proton NMR spectrum of benzene is added in the right panel. Now we can see both the spectra stacked and easy to compare. As expected, in the benzene spectrum, we can see only one peak at delta 7.37. Expand the peaks by left-clicking and dragging on the area covering the peaks. Right-click on the benzene spectrum and choose Integration from the context menu. A window Integration for 1H NMR simulated opens. click on the Apply button and close the window. The integration of the peak corresponds to 6 protons. When we compare the peaks in both the spectra, the chemical shifts in aniline have shifted upfield. This is because the protons in aniline experience more shielding. The two spectra can be merged by clicking on the Click to Combine button. You can locate this button as a black square at the top right corner of the spectrum. The two spectra are now combined into one. This feature can be used to compare the spectra of two or more molecules. Click the Click to Split black square button at the top right corner. This will split the spectrum to the stacking mode. If you want to close any spectrum, first click on the spectrum to activate it. Then click on the cross button on the top right corner. Let us exit the JSpec view window. Click on File menu and choose Exit option. Jmol has a feature to display carbon-13 NMR spectrum. Open the Tools menu and scroll down to Spectra. Then from the sub-menu, click on Simulated 13C Spectrum option. The JSpec view window opens with the carbon-13 spectrum for aniline. Let us expand the peaks to show the splitting of the peaks clearly. On the right panel, carbon-13 spectrum of aniline is displayed. 4 peaks corresponding to 4 sets of carbons are seen. Click on any peak on the spectrum. The corresponding carbons on the 3D model of aniline are highlighted. Click on the carbons on the 3D model. The corresponding peaks are highlighted. The carbon attached to nitrogen and metacarbon are deshielded. Their peaks appear downfield. The orthopara carbons are shielded and hence appear upfield. The spectrum can be saved in various file formats. To save the spectrum, click on the File menu. Select Save As option. There are options in the sub-menu to save as original, JDX, CML and XML file formats. I will choose the original option. A Save dialog box opens. Select a convenient location to save the file. I will choose the location as Documents folder and type the file name as aniline-cnmr. The file will be saved as .jdx file format. In Files of type, choose jcamp-dx files. Click on Save button. This file can be opened in JSpec view and further edits can be made. Spectra can also be exported as PDF and other image file formats. Click on File menu and select Export As option. Here you will find many file options. I will select the PDF option. Print Layout dialog box opens. Here you can change the settings if desired. I will leave them as such and click on Create PDF button. A Save dialog box opens. Select a suitable location and name for the file. I will choose the location as Documents folder and file name as aniline-cnmr-1. Select Files of type as PDF files. Click on the Save button. Title for printing dialog box opens. I will type the title as Simulated Aniline 13C NMR. Click on the OK button. Let us summarize. In this tutorial, we have predicted the proton and carbon-13 NMR spectra for organic molecules using JSpec view, changed the display parameters of the plot, integrated the peaks in the proton NMR spectrum, stacked 2 or more spectra on the panel, combined 2 spectra, saved the spectrum in JDX format, exported the spectrum in PDF format. As an assignment, simulate the proton and carbon-13 NMR spectra for molecules of your choice. Explore more features of the JSpecView interface. The video at the following link summarizes the spoken tutorial project. Please download and watch it. We conduct workshops using spoken tutorials and give certificates. For more details, please contact us. Please post your timed queries in this forum. The Spoken Tutorial project is funded by the Ministry of Education, Government of India. The script for this tutorial is contributed by Snehlata Kalyapan. This is Madhuri Ganpati from IIT Bombay signing off. Thank you for joining.